Good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course, NOC 26 ME 20. So, being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. So, it's a 12-week course. It's a 12-week course, and we are into seventh week of this course. So we have seen modeling of normal shock waves, of expansion waves, and then we saw oblique shocks and how we differentiate between oblique shocks and normal shocks. And in the last week's content, we were discussing modeling of expansion waves, and we discussed oblique shocks also. Right. Now here again we'll be discussing expansion waves and oblique shocks. So this is week number 7. Okay. So half of the course you can say is done. Right. Instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and I am a research scholar here. So pursuing my PhD here and teaching assistant for this NPTEL course. So we shall wait for another 5 minutes to see if somebody joins. If not, we'll just start the session. Thank you. Okay, so we can start with today's session. So there are two lectures in this week's content. Lecture number 16 and lecture number 17. So in lecture number 16, we again discuss this few topics related to oblique shock, and then inferences are there based on this discussion. After that, in lecture number 17, we see some theories and how your flow behaves when we have a blunt body, okay? The kind of shocks that we get. So this is there. Two lectures are there. So first we'll see lecture number. So first we'll see lecture number 16 and questions related to it. Then we'll see lecture number 17 and few questions related to it. Right. So this is there. So let's see first the topics that were there in lecture number 16. So first we have oblique shock waves that has been discussed, right? Then theta beta m curve, this has been discussed, right? Uh, okay. Then inferences are there. Then one topic controlling parameters. So this is there. Then oblique shock property relation. So this is there. So these topics are there. So related to oblique shocks, right? So this was a revision from previous week's content only. Okay. So what we learned about oblique shocks is that if your flow is turning towards itself, right? So you have flow this way. Okay. So if it is turning towards itself, right? So it is moving in this direction. So it is moving towards itself. This will give rise to a oblique shock wave, right? So oblique means, so this is straight, right? This is oblique. So at some angle, right? So your flow direction will be like this, okay? And then also property changes will be there across this oblique shock, okay? So this was basically oblique shock waves, and then there are relations related to oblique shock waves. So this has been revised, right? Then we come to theta beta m curve, right? So the next topic, if you see, is theta beta m curve. So theta beta m curve is there, right? So from your previous lecture, if you see, so this is your theta beta m relation. Tan theta is equal to 2 cot beta m1 square sine square beta minus 1. Okay. So this is there. And then based on this theta beta m curve, you have this curve, right? So the curve is like this. So in this direction, you have deflection angle. In this direction, you have beta. Now, what is deflection angle? This is deflection angle. What is beta? This is beta. Okay. So these are there. So these two angles. Then how the graph behaves, right? Of this relation between theta and beta, also when we have some particular Mach. So it is like this. Okay. Like this. So what happens is with the oh, sorry. So what is there? So in this direction, your Mach number is increasing. Mach is increasing. Now about your deflection angle, if you take one particular deflection angle, right? So let's say I have taken this as one deflection angle. Okay. Now if you draw this parallel to your y-axis, okay, this will cut at 2 points. Let's say this curve is for M1, this is for M2, this is for last one is for M3. So for M1, if you see this for single deflection angle, so theta 1 I'll call it. So for theta 1, you have two at 2 points it cuts. So it means your this equation has two solutions, right? Of your beta when you have M1 is given and theta is given. Okay. So two solutions, right? Now what are what these two solutions correspond to? So these two solutions correspond to two different oblique shock waves, right? So this one is weaker, this one is stronger, right? So these two are there. From graph we can tell this. Okay. Now talking about M1 only, right? So let's say I have some angle theta 2, right? Theta 2. Now for this angle, if you see, for this angle, this line that I have drawn parallel to y-axis, this does not cut the curve, the theta beta curve, which corresponds to your M1. So this does not cut this curve anywhere on this curve. So which means that for this theta value, we don't have any solution. Okay. So for this theta 2, we don't have any solution corresponding to your M1 value, right? So which basically means that not for all theta values you'll have this solution, yeah, an oblique shock wave, right? So there is some value, okay? So this is theta for M Mach 1, right? So this is theta max. So beyond this, if you are going to go, you're not going to get any. oblique shock. Okay. And then what you are going to get? You're going to get it, and so you're going to get a bow shock. Okay. So this is there. So this is inference number one. Okay. One is related to your bow shock. So inference two is related to your two solutions of this theta beta m relation. Okay. So two solutions, and then it states that your weaker solution is natural to us, but then uh, the stronger solution, if we want, then it is related to the back pressure. Okay. So if we are having flow, okay, from here to, let's say the flow is moving from here to here, then the pressure here, right, that we are maintaining, that is basically back pressure. So back pressure we lower down, right? So this has to do with this the stronger oblique shock, right? So this is there. Okay, so this is about this two solutions, right? Two solutions of theta beta m relation. Then inference three, what inference three talks about? So it says that if your beta is related to your mu mac, okay. So if your beta is related to mu mac, then it's a mac wave. First is this. Then it says that if your beta is greater than mu m, then it's an oblique shock. Okay. So this basically is Mach angle, right? This is Mach angle. I hope you remember what is Mach angle. This is sine inverse of 1 by m, right? So this is there. Then this is there. Then related to normal shock. So if your beta is pi by 2, then what we say that it's a normal shock. Okay. So this is your third inference, right? Then your inference 4. What is your inference 4? So inference 4 we can see from our this graph only. So it says that for some particular theta value, okay, deflection angle, if we talk about the weaker solution of this theta beta m curve, okay, if we talk about this weaker oblique shock, then as the Mach is decreasing, okay, your beta value is increasing, okay, your shock Mach, this shock angle is increasing. So this you can see from here only. So for theta 1 only, if you see, okay, so for theta 1, if you see, your this is for your M3, This is for your M2, this is for your M1. Okay. Now if you see here, this is beta 3, this is it's a beta 2, this is here beta 1. Okay. So because beta 1 we have written here, so maybe you can say beta A1, beta A2, beta A3, some notation you can give. So what do you see now here? That your beta A1 is greater than beta A2. Okay. What I'm saying here is beta A1 is greater than beta A2 is greater than beta A3. But also M1 is less than M2 is less than M3. This is so this is the fourth inference. Uh, okay, from your lecture number 16. Right. Okay, so this is it about some issue with the PowerPoint. Maybe I'll just open it once more. So this is it about this particular section. So controlling parameters also, if you understand your theta beta m curve, so this also you can understand. And then oblique shock property relations mostly have been covered in your previous lecture. Okay, so this uh, lecture was basically focusing on your oblique shock waves. Then we have questions. So first question we have here. So please read this question and try to see which option is correct. So question number one, so four options are there. So we have to tell which one is the correct one. Okay. four options are there. First option says that oblique shocks are curved and inclined at an angle to the upstream of the flow. Then it says that oblique shocks are curved and inclined at an angle to the downstream of the flow. Okay, third is these are straight and inclined at an angle to the downstream of the flow. Oblique shocks are straight but inclined at an angle to the upstream of the flow. So first of all, oblique shocks are at an angle to the upstream of the flow. Okay. So out of four options, first option and fourth option has upstream. Okay. Then oblique shocks are curved. A says that, and D says that oblique shocks are straight. So oblique shocks are straight also, and oblique shocks are curved also. Right? So in that case, A and D both are going to be correct options. Okay. So this is question number 1. Then next question, let's see. So this is question number 2. So this should be easy to answer. So question number 2 here says that what is the relation between the angle that an oblique shock makes with the floor and Mach angle? So this I have told. Okay, in the inferences we saw this. So this is there. For an oblique shock, your uh, beta, okay, that shock wave angle is greater than your Mach angle, right? So B option, if you see, this is going to be the correct option. Right? Then next question we can see. Third question is there. So please read this question. Question says that with increase in Mach, what happens to maximum deflection angle? If you will increase the Mach, what will happen to your maximum deflection angle? Mhm. So we'll return to the graph only. So now we see what happens to your maximum deflection angle. So this is your maximum deflection angle 1. Here this is Q max 2. Okay. Then this is Q max 3. So now if you see this, so this basically means that if you are going to increase the Mach number, okay, let's say we have some Mach 2, then we are increasing it to Mach 3. So this deflection angle for which we are going to get an oblique shock, for which your flow is going to remain attached, okay, for which you are not going to get any bow shock. So this deflection angle you can increase. So if your Mach is increasing, your this deflection angle for which you can get an oblique shock, attached oblique shock, so this will increase. Okay. So here. So like what happens to the maximum deflection only? So it increases. So this is the. Then moving on to next question. For a question number 4. So it says that for a weak oblique shock with increase in Mach, what happens to the shock wave angle? So this is there. The question talks about weak oblique shock. Then it says that your Mach is increasing. So what will happen to shock wave angle? Again, going back to the this graph, it talks about uh, weak oblique shocks. So if you see your weak oblique shocks, so with increase in Mach. So if you are moving from M1 to M3, so this if you see, if you're moving from here to here, okay. If you are moving from M1 to M3, your shock wave angle is going to decrease. Okay. So because beta A3 is less than beta A2 is less than beta A1. Right? So this is good. So shock wave angle is going to decrease. this was the question. Right? So this decreases. Okay. And why it decreases that we have seen from our theta beta curve. Okay. Then moving on to next question. This talks about bow shots. So what are bow shocks? So when you were talking about this, if flow is happening in this direction, okay, and this theta is greater than your uh, theta max. So when it's less, then you get these types of oblique shocks. Right? So this is basically a wedge. I hope you understand wedge. What is wedge? Okay. So in 3D, if you see, it is like this. Structure something like this. Then flow is happening in this direction. Okay, so this basically is your wedge. Okay. And we are just showing this cross section. This cross section we are showing here. Okay. So this front basically, this front or this basically is this point. Right. So this is there. So if your theta is greater than your theta max, then what will happen? You will not get this attached kind of. Okay. You will get a shot something like this. This basically is your bow shot. Okay. Then now what the question asks? The question asks here that bow shots are dash and dash. They are straight and attached. They are straight and detached. They are curved and attached. They are curved and detached. So they are first of all detached. Okay, so there is gap between this point and this point. There is gap. So these are detached. Okay, but then they are curved also. Okay. So in that case, D option comes out to be the correct option. Then next question. Let's see. It's a true or a false type of question. It says that when there is 0 degree flow deflection angle, the strong shock takes the shape of normal shock. Is it correct or not? When there is 0 degree deflection angle, beta is zero, sorry, then what will happen to your strong shock? Now you see the graph, what will happen to your strong shock? Okay, so this solution, the solution that I am this on which I am drawing this thick line. So this basically for M1 mag, this corresponds to your strong oblique shock. Now talking about theta, if you see theta is 0 degree if you keep, okay. If you keep your theta 0 degree, in that case, this curve relates theta 0 to beta equals to 90 degree for your strong shock. Okay. So here what will happen is your beta will be 90 degrees. Okay. So when your beta is 90 degrees, in that case, this acts as a normal shock. So in that case, this is a true statement, correct statement. Okay. Then next question. Again, true or false type of question. When the normal component of Mach number ahead of the shock wave increases, the strength of shock wave also increases. So is that correct or not? So now what is this normal component? I will show you from your previous week's discussion. So this basically is your um, this is the so now for your this oblique shock, for your this oblique shock. You have this M1 back of the upstream flow. Okay, and then its normal components are there. Mn1 is the normal component. Then there is tangential component also. Velocity component is V1. Right? And then downstream, if you see, the tangential component is V2 and your normal component is V. Okay? And the corresponding MAC is Mn2. So I hope you remember this figure. So obviously, because see, when we are talking about only normal component, right? So this works as a normal shock. So in normal shock, as your Mach number is increasing, your strength of your shock is increasing. So if we are talking about just normal component, so if the normal component is increasing, the strength of this shock wave is also going to increase. Okay, so this is a true statement there. This is the question number 7. Then lecture number 17 is there. So the topics of lecture number 17 we'll discuss one by one. So first we have expansion wave theory, beam shock theory, and supersonic flow over bridges, attached and detached shock on a supersonic symmetrical wedge, finite wedge, unsymmetrical wedge, supersonic flow with bones. Okay. And there are other topics also. Shock expansion theory and supersonic flow with blind body. So these are there. So expansion wave theory is discussed. Okay, so this is revision only, right? If your flow is moving away from it, okay, then you're going to get expansion fan. And then we saw that this fan extends to some angle only that we call as fan angle. Okay, this was your deflection angle. Okay? And then two back angles also there that were mentioned. Then oblique shock theory again has been revised. So this oblique shock theory we have seen in just in the previous lecture. We have again seen this oblique shock theory and inferences out of the theta beta m curve we saw. Then we have supersonic flow over wedges. This we can see supersonic flow over wedges. So this is there. So I have already told you what is a wedge. Okay. That basically is this. This structure basically is a wedge. Okay, sorry for the glitch. So I was facing some interpretation. So I was talking about lecture number 17 and supersonic flow over wedges. So I was talking about wedge. So I'm a bit struggling to draw a 3D wedge, but you can understand that it's a basically cross section. Okay, so it's a triangular cross section. So if you extend it in one more dimension, so you'll get a wedge. Okay. So in this direction perpendicular to the sheet, if you are going to draw this wedge, okay, so that basically is a wedge. Then, then if your flow is moving in this direction, as I am pointing out, so what will happen is, so this wedge will act as for flow. It will direct the flow towards itself. Okay, this is going to direct the flow towards itself. Okay. So if it is going to direct the flow towards itself, in that case, we'll get oblique shocks. This basically is your supersonic flow over wedges. And in case your theta angle, if your theta is greater than theta max, what is going to happen in that case? You're going to get a detached shock. Right? So this theta is greater than theta max. is greater than 3 times. Now what we are going to get here is we are going to get here a bow shot. In front we are going to get this. So if your flow is in this direction, okay. So in front of this wedge, you'll get a bow shock, okay. And then there is with dotted lines, this region has been shown. So this region has been shown. So what happens? This the region in this region, your MAC is less than 1, okay, which is related to your strong oblique shocks. Okay? And then at this dotted line, okay, your MAC is sonic, okay, 1. Then beyond this, if you go, then your solution is of weak oblique shocks. Okay, where your MAC is greater than 1, but it will be less than your M1. Okay, because we have an oblique shock. So this is there. Okay, so this is the detached. Detached. Right, so this is there. So this is your symmetric wedge. Then there is finite wedge. So what happens in your finite wedge? If you see the finite wedge, okay, so this you were talking that if this keeps on extending, so this was this case. Now we are saying that this wedge is going to be confined to some distance. Okay. So what happens here is, so this is your wedge, right? This is your wedge. These are walls. So what happens here is that your flow is moving in this direction. Okay. Then this deflection is there. Okay. Then this is there. So this M2, this is M3. This is magnet. This is straight oblique shock. And this here is your curved oblique shock. So in actual, this happens here, right? So for your this wedge, okay, finite wedge, because it has some length. So for this finite wedge, you are going to get first of all a straight oblique shock. Then after some point, this becomes curved, okay, because of this finite nature of the wedge. So this is your curved oblique shock. Okay. Then after that, what we get is a Mach wave. Okay. So from the experiments, this is there. Then if you talk about flow, so first you had Mach 1, then downstream of your oblique shock, you have Mach 2. Okay. Then this flow downstream of your oblique shock, again, it is diverted when your finite wedge ends, when your wedge ends. Okay. And this is a what type of corner? So the flow is moving towards itself or away from itself. So the flow is basically moving away from itself, right? It's a convex corner. So we will have at this deflection point expansion waves, and then this flow will again move parallel to the this your wall. So this is there in your finite wedge. Then you have unsymmetric wedge. So one point here is that so unsymmetric wedge basically is when your so if you have this, when your theta one is not equal to theta two, it, then oblique shocks are going to be different. This is there. But then if you have the flow, so if flow is in this direction, that will be. But then if the flow is in such direction at some angle of attack, that your these two deflection angles become same. In that case, these oblique shocks that we are going to get, they are going to be same nature. Okay, so this is about unsymmetric wedge. Then what is there? There was supersonic flow with poles. So cone was 2D. Okay. Sorry, wedge was 2D. Now, what is cone? Cone basically is, you all know, right? So now if we have a flow for a cone and we compare it with the wedge. So what happens here is, this is theta, this is theta. So what happens here is, first difference is that for same Mach number, okay, the maximum deflection angle that is allowed. For cone, it is going to be higher. For wedge, it is going to be lower. Why so? Because in case of cones, you have relieving effect. Okay, because of relieving effect, if you talk about the strength of oblique shock, in case of your cones, it is going to be less. In case of your wedge, it is going to be more. Okay. Then static pressure, if you see, so static pressure downstream of your oblique shock, if you see, for your cone is going to be less than static pressure for your wedge. Again, the reason is relieving effect. Okay. The 3D effect. So this is there for your supersonic flow over cones. Then shock expansion theory is there. What does your shock expansion theory say? So shock expansion theory you apply to diamond shaped airfoil. Okay, diamond shaped airfoil where you have this as the thickness. Okay, so, and this you have as the chord. Okay, then here you are going to get oblique shocks. Here you are going to get expansion fan, and here again you are going to get oblique shock. Oblique shock, expansion fan, oblique shock. So P1, P2, P3, P4, something like this. So So oblique shock is going to increase your static pressure, and then expansion fan is going to decrease your pressure. We have seen in expansion fans discussion that what happens to your static properties. Okay. Total properties remain same. So, diamond shape, I hope this is clear. So this again is a 2D section of uh, this diamond shaped structure. Mm, yes, where this is the leading edge, this is the trailing edge. Right? What else? Okay, so this is there. Then this here gives rise to wave drag. Okay, so these oblique shocks, expansion fan, in combination, they give rise to wave drag. Now, drag per unit span, span we denote by P. Okay, this expression for this basically is P2 minus P3 into thickness of your whole airfoil. Okay, diamond shaped airfoil. So if you have read studied the nomenclature of your airfoil, right? So these subsonic airfoils, if you see, so this is your chord, right? So chord here is this, then maximum thickness somewhere. Okay, T, that is T. So this is here. So this with this chord and thickness are going mentioned. So this is there about drag. Then supersonic flow over blunt bodies. When supersonic flow over blunt body, what happens? So in a supersonic flow over blunt body, what happens is that you get the whole range of your the shock waves. Okay. So this is your blunt body. Here what happens is So your Mac is less than 1. Okay. This is our initial Mac. So here your Mac is greater than 1. And this is your sonic line. So this we are going to see with this beta versus theta graph. It is like this here. So A point basically is your center point uh, towards axis, right? So here you are going to see a normal shock, okay, A point. Then if you move slightly away from your this center line, then you are going to get a strong oblique shock, okay. Then beyond C, if you are going to move, then you start getting these weak oblique shock rays, right? Where your MAC is greater than 1. So in your strong region, your MAC is going to be less than 1. Okay. Then eventually crossing D, you have E where you are going to have your MAC wave. So in your blunt body, supersonic flow or blunt body, you get all these waves. Then we'll move on to questions. Okay. So it says that question number 8, the pressure jump across the oblique shock induces wave drag. Okay. So whether this is true or false, it does this induces wave drag, right? So in the this shock expansion theory, this is there that from oblique shocks you are going to get this wave drag. And in the design of this such airfoils, supersonic airfoils, what do we want? We want this that this wave drag is minimal. Okay. So question number 9, in case of symmetric wedge, when the semi-wedge angle is higher than the maximum flow deflection angle, the flow in the vicinity of nose is supersonic. So whether this is correct or not, so this is a false statement, right? We have seen that your MAC is less than a 1 here in this region. Okay, MAC is M2 is less than 1. So this is a false statement. Then for a specific Mach value, the static pressure rise across an oblique shock is higher in case of conical shape when compared with the wedge. Static pressure rise across oblique shock is higher in case of conical shape when compared with this is false, right? Because we have the relieving effect because of which this is less for your conical shapes. Then this question is there for a specific Mach and deflection angle. The Mach is given and deflection angle is given. The shock wave angle in case of a cone is smaller than for a wedge. Whether this is correct or not. So this is a correct statement. Okay. The shock wave angle beta is less in case of a cone. Then next question. Is there in case of a blunt body near the nose, the shock is normal to the free stream and gradually becomes oblique away from the nose. So whether this is correct statement or not. So this again is correct statement, right? So we have seen okay, in this diagram we have seen how from shock first at A moves to B, then to point C, then D, then eventually E. Okay, so this is there. Then we have few numerical questions. So for this, first I'll give you some data. So M1, M2, T2 by T1, and T2 by T1. So this I'll give. So for 1.95, 1.97, 1.99, this I'll give. Maybe I'll keep it with 2 digits only. So this data is there. Okay. Then beta is there. Okay. So this is related to an oblique shock. Gamma is there. R is there. T1, T1, V1. This is there. Then first of all, it says that. Okay. Let's see the question. Find the static pressure at downstream of flow. So this is for an oblique shock. This is the okay. So question number 13 to 16. V1 is there. Beta is 40 degree. Gamma is 1.4. R is 287 joule per kg Kelvin. So P1 is 98 kilopascal. P1 is 295 Kelvin. And then V1 is 1070 meter per second. So this is there. Then the question here asks that find the static pressure at the downstream of the flow. For the static pressure, we need to find out first of all. So because this table is given, right? So P2 by P1 is given. P1 we have. P2 we need to find out. Okay. So now this ratio is given, right? But then which Mach uh, is of our concern, right? So that we'll have to see. So from velocity term, we will calculate that. So let's see. Question number 13, solution. A1 will calculate gamma RT1. T1 is 295. So 1.4 into 287 into 295. We'll take under root. So this will come out to be 344.28 meter per second. And calculate Mach from here. Mach, if you calculate, Mach will be V1 by A1. So V1 is 1070. A1 is 344.28. So this comes out to be 3.10. So this is your M1. Then, so because your normal component only is of concern in the oblique shocks, so I'll calculate Mn1. Okay. So related to normal component only, we have to see this pressure rise, static pressure rise. So Mn1 will be M1 sine beta. Okay. So this velocity triangle you can see. Velocity triangle has been drawn here. Okay. So this velocity triangle you can see to get your normal component. Okay. So M1 sine beta. Now M1 is 3.10, beta is 40 degrees. So this comes out to be 1.99. Now corresponding to this, for Mn1 equals to 1.99, your E2 by P1 is, now you see, your P2 by P1 is 4.45 and your T2 by T1 is 1.67. So this is there. Now the use of this table is done, right? That was given to us. Only this we have to use. So now we can calculate implies static pressure rate. E2 is 4.45 into P1 is equal to 4.45 into P1. Right? P1 is your 98 kilopascal. So 4.45 into 98. Please calculate. This is 436.1. So this is there. Sorry. This is kilopascal. Pressure in kilopascal. Then next question is there. Question number 14 is there. So this I'm getting is 436.1. Find the downstream temperature. This also we can calculate. E2 is, you see, 1.67 into T1 into 1.67 into what is T1? T1 is 295. So let's calculate this 1.67 into 295, 492.65 Kelvin. So the answer is 492.65 Kelvin. Find the flow deflection angle. Now to find the flow deflection angle, what do we need to do? So this also is not lengthy. So what we will do is so first we'll so let's go back to the diagram. Okay, we can copy this again here. What is the what the we have it again. Take it from here. So we'll use this. Now, because in the tangential direction there is no velocity change. Okay, so your P1 is so my mic was mute for few minutes, many minutes. Anyways, so V1 is equal to V2. So this is equal to 815.94 meter per second. Now we have V1 for this, V2 for this. Now U2 we need to calculate. So U2 is Mn2 A2. Okay, normal component, then multiplied by the acoustic speed. So normal component, how we can calculate? So from the again from this table, right? Again from this table, you see this is 0.57. Okay, this is 0.57. So 0.57. So this is 0.57 into A2. A2 is gamma R T2. T2 we have here you see people we have here 492.65. So this is 0.57 into 1.4 into 287 into is 492.65. 492.65. So we'll have to calculate this. 1.4 into 287 into 492.65. So this is 444.91 into 0.57. So this is 253.59. This I'm getting. Then tan beta minus theta is equal to 253.59 divided by 815.94. 815 815.94. So then tan inverse we need to calculate. Tan inverse of 253.59 divided by 815.94. 15.94. This comes out to be 17.26. Is theta minus theta is equal to 17.26, implies theta is equal to beta minus 17.26, 40 minus 17.26. This is 23.74 degrees. This is there. Then last question. Find the velocity at the downstream of the flow. At the downstream of the flow, we need to find out the velocity. So this will be v2 u2 square plus v2 square. So this is 253.59 square plus 815.94 square. So this will come out to be sorry, this is not 815. Yes, 815.94. This is 854.43. So this is there, 854.43 meters per second. Okay. So it was initially 1070, then it has been reduced to this around 800 something. So this is it about today's session. I'll just conclude this session. So expansion waves and oblique shocks. Two lectures were there, lecture number 16 and 17. Uh, on the topic of expansion waves and oblique shocks, these were third and fourth. So here in lecture number 16, there were oblique shocks that were discussed. So in oblique shocks, theta beta and relation basically, and the curve related to it and inferences from it. So this was discussed. And then in lecture number 17, we saw we revised oblique shocks, expansion wave theory. Then we saw flow over wedges. So flow over a finite wedge, flow over infinite wedge, flow over a blunt body, flow over a cone. So what is the relieving effect in terms of cone and how it affects the properties across the uh, oblique shock? And then how this relieving, because of relieving effect, the static pressure increase for oblique shock in cones is low in when compared with your wedges. Right? So this all we discussed in this session. So next session again will be on coming Tuesday, right? So I have preponed this session because of some reasons. The next session again we will be taking on Tuesdays only from 6 to 8 p.m. All right. Thank you. Thanks for watching this session.